Hello all. We are embarking on our third unit in grade 11 math in functions. And as a lot of our units will do this year, this one will have to do with functions. Our first unit, we looked at an introduction to functions, and you were introduced to four basic functions and function notation. We took a little time out and went with our second unit, which is more algebra based, but now unit 3 and indeed unit 4, unit 5, and unit 6 will all have a lot to do with functions. All right. Now, when we looked in unit 1, we looked at the four basic functions, and you were given the simplest version of each function. And so what I need you to do is, first of all, I need you to start a note. And I'll bring mine up here. And in a second, you can pause it and write down what we have here. But of course, we have the title of the note that we're looking into this unit, which is concentrating on transformations of functions. What happens when we go beyond just the simplest function? What about different versions of each function? And so at the top here, I'm asking you to recall that you learned four basic functions. And so in a second, when you pause and start writing stuff down, I want you to actually go back and do what I did here. Name the function, remind yourself of the function, its name, its basic equation. And this is so vital. You must know the key points, right? For each one, you were asked to know some key points. And so you should copy those down. Maybe even a quick rough, this is a pretty rough on my part, sketch of the graph, just reminding yourself what it looks like, what it does. Okay, so you are now going to pause and you are going to fill in the other three functions: names, points, quick graph. So you have paused, you have three other functions filled in, and we're back. And what I want to do now is I want to as well build on some previous knowledge that in grade 10, we spent tons of time exploring the quadratic function, right? And we learned about it in several forms, but when we look at the quadratic function in vertex form, this is going to be pretty instructive of, and similar to how we're going to explore our functions in this unit, okay? The four different functions that we're gonna transform and work with. So if I bring up this graph here from Desmos, then you see here's the quadratic function, right? And here it is, it's in its basic shape, right? This is the y equals x squared. You see the key points are actually highlighted here. And you'll notice as well that up here I've got kind of a generic written out vertex form, at least is the way we learned it in grade 10, with an A value. Now, there's a D here and a C here. Last year, we technically learned that they were called H and K. Different textbooks, different courses name them different things. The most important part is where they are, right? And you recall that D and C related very closely, of course, to the vertex, where the vertex of the quadratic function was. All right, so now you'll notice as well that right now on Desmos, I have A and D and C set to 1, 0, and 0. And if you plug in 1 here, 0 there, 0 there, you realize, okay, that works out just to y equals x squared, which is technically in vertex form. It's technically in all the forms. So what I'm going to do is I'm going to pop up a different quadratic function, okay, with a different quadratic function equation. So I'm going to graph the function y equals 3 bracket x minus 2 squared minus 4, right? And so we're going to compare that to our original y equals x squared and see what a number here in the, what we're calling the A spot, and a number here in the D spot, and a number here in the C spot do, all right? So if we take a look at Desmos, here it is. You see over here that I've made A equals 3. Notice that D here, I didn't pop in D equals -2. I popped in D as 2 because that's what gives me x minus 2, right? So just a little thing that's going to catch a couple of you off guard, excuse me, is that when D is 2, you get x minus 2, right? And then C is -4. So I also left an imprint here, or like, I guess a dotted line that showed the original. And I want you to look at our new graph here and our old graph and see if you can describe in your head, okay, what did these numbers do and which one did them, right? How did I get from my original graph to this new graph, which is, I guess, on your screen down here, right? What happened to the shape of it? Well, we would obviously say that this thing got a little skinnier, looks like it got a little skinnier. Maybe if you were in my class in grade 10, you remember that I said, yeah, I don't actually say that it's skinnier. Maybe you remember something different about it. But definitely, right, it's a little tighter in. It looks a little different. This thing has also been moved, right? It's been moved obviously down and it's been moved a little bit to the right, right? So I want you to look again at so when A is 3, so if there's a 3 here and a 2 here and a -4 here, this thing gets a little skinnier, it moves to the right and it moves down, right? And I think most of you can recognize which number tells you how much of which thing is happening, okay? I'm going to try a different one now. I think I'm going to, let's see. Try y equals -1/4 x plus 3 squared plus 6. Okay, y equals -1/4 x plus 3 squared plus 6. And now we can see on screen this this function. You see this thing's been widened out a bit. It's been flipped. That's what I mean. Maybe the first obvious thing. This thing is now upside down or opening down. Okay. It's also right. It's shoved to the left. That's my left. But it's been shoved to the left, and the vertex at least has been moved up. Right. The vertex was here, and on my screen anyway, we kind of went up and to the left. Right. So I want to as well point out just, okay, so what did I plug in here? I plugged in that A equals -1/4. I had to put it as decimal. D in this case is -3, right? -3 gave me an x plus 3 here because the pattern is x minus D, and then the C being plus 6. So now I think what I'm going to do is I'm going to actually pull this thing back to its original shape. I'm going to set A back to 0. Nope, A back to 1, sorry. D back to 0. And as I'm doing it, you can see this thing is actually aligning back where it needs to go. Right? And I can play around with these sliders a little bit. And when you watch this time, or when I do this, I want you to watch what happens with the points that I have, right? So for example, we'll start with the C value here. As I swing C to a negative number, it goes, the farther I go negative, the farther it moves down. The farther I move positive, right? C plus 4 moves this thing up. Looks like C value, the C value in this thing decides whether this thing is translated, shifted up or down, as opposed to the D value. And now I'm going to put in D equals 4. I'm going to slide my slider over from D equals 0 equals to D equals 4. Which way is this thing going to move? It's going to move to the right as I increase D. So as D gets bigger than 0, the graph is translated to the right. Now notice as well, don't forget that in the equation, when I put in D equals 4, it's going to read x minus 4, right? But I'm actually putting in a positive D value. As opposed to, and I'll slide it back, when I make D equals -5, this thing is sliding to the left, right? Translating to the left. So D and C are things that translate the graph, left and right, up and down. A is right now 1. If I make A bigger and bigger and bigger, right, it looks So I mean, everyone's first instinct is to say, oh, it's getting skinnier. But I want you to see what happens with the points, right? The green and red and orange and blue points. As I make A bigger and bigger, those points are actually moving. Looks like they're getting closer together, but they're not. They're actually just going straight up. This thing is looking skinnier, not because it's gotten squished this way. It's actually getting stretched this way. It's actually getting pulled up, and it makes it look skinnier, right? If you ever pulled a piece of taffy or gum or silly putty or whatever, right? When you stretch it, it actually gets skinnier. So, but I want you to get in the habit of when A is getting bigger and bigger and bigger, you are saying that this thing is getting stretched or expanded vertically. Okay. And when I make A, now if I play around between A equals 1 and A equals 0, so A is a fraction like a half or a quarter, then we get kind of the opposite thing happening. It looks like it's getting wider, but actually if you watch, and I'll do it again, as you watch what happens from A equals 1, those points are going straight down again. They're getting squished down. So it looks like things look like it's getting pulled out, but it's not. It's actually getting pushed down, and that's squishing it wider, right? Same thing. If you have a ball of silly putty and you squish it down, it flattens out, right? Same thing is happening with this graph. So I want you to have in mind, okay, so what's going when A is a number bigger than 1, this thing is getting stretched vertically. When A is somewhere less than 1, but not negative, right? So somewhere between 1 and 0, this thing is getting smushed down, compressed vertically. And then when A gets negative, we've already seen this, or you saw this last year, that if I use a negative value for A, right, a big negative value for A, then it's stretched, but it's also flipped, reflected. Okay, so we would say this thing is reflected vertically. Or one way we would say this is actually reflected in the x-axis, right? The x-axis is the horizontal axis. This thing is like reflected in or reflected over the x-axis. When A is negative, this is reflected over the x-axis. And of course, if A is a big negative number, then it's reflected over the x-axis and stretched vertically, right? Looks skinny, but it's actually stretched vertically. And when A is a smaller number, like a fraction of like 1/2 or a quarter, right? So negative a quarter or negative a third, right around there, right? This thing's actually squished down. So it's A is negative a third would give me a graph that is reflected over the x-axis, or reflected vertically is an easier way to say it, I guess, but also compressed vertically. Right? And we actually treat those two things like two different things, A being negative and A being a number between 0 and 1, or A being negative and A being a number greater than 1. So we treat those as two different transformations, the vertical flip or the vertical reflection, and the either compression or the stretch. We treat those as two different things. Okay. Now, we don't need to write all of that down just now. Maybe I should take a pause for a second and think about that. And I think I'm going to maybe modify what I just said. Actually, you should make some notes about this, right? So you should note what happens to the quadratic function when A gets greater than 1, when A gets less, or when A is somewhere between 0 and 1, when A is negative, when D is either greater than 1 or D is less than 1, when C is greater than 1 or C is less than 1, right? In another way you could do this, you could point at each of these things, right? And you would say, well, this 6, for example, this 6 translated this graph to the or up, right? And this 3 here translated the graph which direction? Which direction did it translate the graph when we put in x plus 3 as our equation? And this 1/4, what did that do to the graph? Did that compress it? Did it stretch it vertically? And what did this negative do? Okay, so all of those, so you have to have an idea of what each one of these things did to the graph. Translations, um, uh, translations, compressions, reflections, expansions. All of these are types of transformations that you need to name. So you should take a minute now and pause and record if you haven't already. In all of these cases, what happens? What happened? Okay, that's all great, and that's all going to be actually really, really important. And you'll be doing a little bit more work with this type of thing with some other functions. But right now, we have to actually add one more layer to this, okay? So we would say that the function y equals x squared is transformed to y equals a. Don't write this down just yet. Let me write it down. X plus x minus d squared plus c. Okay, we just went over this, and this is what you've seen before. There's actually one more level of complexity that we're going to add. We're going to add one more letter in there. So it's going to be transformed to y equals a k times x minus d squared plus c. Right? And you're going to explore a little bit later on. What does k end up doing to the graph? Right? We know what we have a bit of an idea what happens when we manipulate a, when we manipulate d and c, and now I've thrown in this k value. What does that do? Now let's just as well say, well, we've looked at some other functions. For example, the function, the absolute function. Y absolute x is transformed to y equals a absolute k x minus d plus c. You'll notice that the pattern looks very, very similar. All of these values, the a, the k, the d, and the c, they get plunked into the equation in a similar, or in basically the exact same place as they would if it was a quadratic function. We looked at, of course, or you need to know about the radical root function, right? That's transformed to y equals a square root of k x minus d plus c, right? Make sure your square root specifically includes the k and the x and the d, right? But, and you'll notice that in all these things, function, right? The k and the d are always going to be in with the x in kind of the functional part of the function. The a is always going to be a multiplier or a coefficient out in front of the function, and the c is always going to be added on to the function. Y, and the last one we looked at is the rational function, right? Or the reciprocal function, if you prefer, and we write it this way. Now, of course, again, we have an x, and k is going to be a multiplier. D is going to be subtracted from the x. A is going to be a multiplier that goes in front of the whole thing, or if I actually write it on top most of the time because that's where it would end up, or where it will end up when you multiply it times the fraction. And then we have plus c here. All right, so far we have this k, which is in the equation, which will transform the equation, and I haven't showed you how yet. I'm going to actually ask you to explore that a bit. Before we do that, I have to introduce, or at least apply this. So now we've applied it specifically in 4 different functions: quadratic, absolute, radical, rational. Transformations can be applied to any function, right? And this is going to mess some people up. It always does every year, and so I'm just going to ask you to do your best to see if you can understand what's going on here. The generic function f at x. So this means any function, okay? I didn't tell you which function it is. This could represent the, it could be that, f at x equals x squared, or it could be that f at x equals 1 over x. In that case, f at x would be the quadratic function, or f at x would be the rational function. It could also be some random looking function like I gave you right on your first test. Could be that this function is just a collection of dots, right? It could be, or it could be, you know, some kind of weird line looking thing, something like this. Okay, it doesn't matter because what we're talking about here is how transformations will affect any function, right? So if I have a generic function that's f at x, then the graph of that function, whether it's the quadratic function or the rational function or some random looking function, it's just graphed as y equals f at x. Okay, so anytime you see y equals f at x, that's really just saying the graph of the function. And so therefore, the generic function y equals f at x will be transformed to y or f at x with a, k, d, and c in it, right? So the whole function will get multiplied by a. There will be a k in with the d. The k and the d will be in there with the x, and you will have a plus c. Now you're going to see this a bunch of times in your assignments and stuff. You'll maybe see that y equals 4 f at 3 x plus 2 minus 4, right? And sometimes it won't even tell you what the function is. Sometimes it'll just say, hey, there's a function, and this is what happened to it. Describe the transformations. And you don't even have to know what the function is, as long as you recognize that, oh, 4, that's an a value. This 3 is a k value. This 2 is a d value. This 4 is a c value, right? I guess the 2 is a negative 2, actually, if it's a d value. This f, of course, is just part of f at x. Okay, it's not a variable. It's just the function. Okay, you'll see it, and you'll. And the one thing I'm asking you now is see if you can somewhere implant in your memory that if you see f bracket, right? F bracket, that just means that you're working in function notation, and it hasn't necessarily specified what the function is. It could be that it tells you, oh, it's this function, or it's this function, or it could just show you a picture of the graph and say, oh, it's y equals f at x, and this is f at x. Regardless, you just have to know what all of the transformation pieces will do to the function or do to any function. So to summarize and to kind of look ahead, like you might get a question like this. Describe, oops. The transformations on the, we'll go with the rational function, y equals 1x. If it, instead of what being y equals 1 over x, becomes y equals -3 over a quarter or a half x minus 1, that's all in the fraction, minus 2. Okay, and you don't have to be able to do that today. We haven't even really established for sure what all these things mean, especially the k value, but you need to be able to spot the fact that, oh, there's an a value, it's -3. And hopefully you already start to have an idea. I think I know what -3 might do. I know what the negative part might do. I know what the 3 might do if it does the same thing that it does to the quadratic function, which it does. Okay, there's a k value in there. It's 1/2. We haven't talked about what that does yet, but you do as well see, oh, there's a d value of 1. What's that going to do to the graph if it does the same thing that it does to the quadratic function? It's got a c value of -2. What is that going to do to this graph comparatively? What's going to be different in this graph compared to this graph because, for example, this -2 is here? All right, we're not going to answer this question now, but this might be the type of question you might need to answer. And in fact, tacked onto this would be, okay, graph an accurate representation of this function based on the transformations that you know. Okay, based on the fact that you know what this looks like, and based on the fact that you know all of the transformations that are in here will do to this thing. Okay, you're going to find in EDSB an assignment which is going to invite you to look at a few graphs in Desmos that I've prepared. Okay, looks similar to what you looked at or what we looked in this video about the sliders and what they did to the quadratic function. So I've prepared 4 of them. I've prepared, and in each one you can slide A, C, or D, and C, and K as well. Okay, so if you look at the assignment, you'll see that I'm asking you to specifically first investigate what happens when you play around with these things in the radical function. Okay, and I think you should be able to see a transformation for each one of the things that you play around with. And then I'm going to ask you to actually explore the other 3 and see if all of the transformations that you discovered for the radical function, see if they all hold true for all of the functions, or do some of the transformations not seem to be affected, or do some of the functions not seem to be affected by all of the transformations? And then when we get together on Wednesday, we'll discuss a little bit about that. But I do expect you to do the assignment. I do expect you to hand something in to demonstrate that you have done it. And I think that's it for now. So check EDSB for the assignment. Check EDSB tomorrow for maybe some follow-up on that, and that will be it. All right. Good luck with this, and we'll see you soon.